How would you go about getting liters of a gas in non-standard temperature conditions? Well, you would use the ideal gas law equation. And so in the following pages, we will be doing that and using our knowledge of stoichiometry and putting it all together. Now, I think you'll find it not a whole lot more difficult than working regular stoichiometric problems. So let's get started on it. And we will be using the same flow chart that we have before in the past. And instead of using Avogadro's number, once we get converted to moles, we'll be using the ideal gas law equation. PV is equal to nRT. So we'll be able to predict volumes of gases involved in chemical reactions under varying temperatures and pressures. And here we have an example problem. And to save ourselves a little time, I went ahead and balanced the equation that we'll be using in the problem. And it reads here, how many liters of carbon dioxide, okay, so this is what we're solving for, liters of carbon dioxide, can be produced if 110 grams of hexane react with excess oxygen at 1.5 atmospheres and 30 degrees C. So you'll see here that we have instead of the standard conditions, STP, we have a temperature and a pressure that varies from that. And so let's get started and we'll write down what we're given. That's always a good place to start. We have 110.5 grams of hexane, C6H14. So we're going to go from grams to moles, moles back to grams, and then finally, moles to moles here, and then finally we will convert our molar amount to a volume amount using PV is equal to nRT. So we'll just rearrange that. Volume will be equal to nRT over the pressure. Okay. So, but first we've got to go from grams to moles. So grams will go on the bottom per 1 mole of hexane. And I looked that up for us. It's 86 grams of hexane per 1 mole of the same. And then we're here at the moles. So we'll have to go to moles of our new product. And so whatever you start off with always goes on the bottom of your conversion factor. So we'll have moles of C6H14 on the bottom. And then we'll have moles of our carbon dioxide on the top. All right, so whenever you go from moles to moles, use the balanced equation and the coefficients off of that. So let's pick off our carbon dioxide first. We have 12 moles of carbon dioxide for every 2 moles of our C6H14 or hexane. So when we do that calculations, it's 110.5 times 12 divided by 86 times 2. So here, now that we have our molar amount, we can use our PV is equal to nRT to adjust the volume for those conditions. So the volume here will be equal to 7.71. That's our mole amount. That's the mole amount here. Our R value is 0.0821 liters atmospheres, Kelvin mole. That's our units for our R value. And then we have a temperature of 30 degrees C. And 30 degrees C plus 273, remember you have to convert that to Kelvin, will be 303 kelvins. So you have all that as your top fraction, and you'll divide that by your pressure. We did R and T, and we'll divide that by our pressure. And our pressure is given as 1.5 atmospheres. Okay, so let's do the math there. And when we do the math there, liters of our carbon dioxide. Okay, so there's our final answer there. So these gas law stoichiometric problems are not any more difficult than the ones that we did before, but the main thing that you've got to keep in mind is that once you solve for moles, you have to plug it in to PV is equal to nRT to solve for either a pressure or volume or whatever they ask you to solve for. And the thing to keep in mind there is to watch your units. Make sure your units match your R value. Liters, atmospheres, Kelvin, mole.